In today's lecture, I'd like to talk to you about small numbers, large numbers, and very large numbers, and how to use some important approximations for thermodynamics. So first, let's talk about what we're going to talk about, right? Let's define our terms. So small numbers are everyday numbers like 42, right? The answer to life, the universe, and everything. Or 102, or 1,022, or 1,000,002, right? So large numbers are numbers like 10 to the 10th, 10 to the 23rd, 10 to the 46th. Now, the difference in between these things is that you can add a small number to a large number and it doesn't really change it. The large number is still pretty much the same as it was before you added the small number to it. So for example, let's say you have a mole of things, 10 to the 23rd, and to that mole you add 1,000 things. Well, 10 to the 23rd plus 1,000 is still pretty much 10 to the 23rd. So you make large numbers by raising a small number to the power of a small number, or maybe even doing the factorial of a small number, right? So that's how you get them. So now, large numbers like 10 to the 23rd, let's compare that to very large numbers. Very large numbers would be 10 to the power of 10 to the 23rd. Okay, so that's really big, right? You can make a very large number by raising a number or a large number to the power of a large number. Another way to do it is by using a factorial. So if you do a large number factorial, that's going to be a very large number. Now, you can multiply a large number by a very large number, and the very large number doesn't change pretty much at all. And adding, forget about it, right? So, as an example of this, let's talk about that very large number of 10 to the power of 10 to the 23rd. And then let's multiply that very large number times 10 to the 23rd. Now remember that when you multiply things with the same base and then have different powers, what you do is you add the powers together. So 10 to the 23rd power times 10 to the 23rd would be 10 to the power of 10 to the 23rd plus 23. Yeah. Adding 23 to 10 to the 23rd, it doesn't change anything. So you've still pretty much got, excuse me, this is a typo, 10 to the 10 to the 23rd, right? Doesn't really change it. So those are some approximations that you might be using, for example, in some of the problems that you work in thermodynamics. Now, one way to make large numbers and very large numbers more manageable is to take the logarithm of them and deal with the logarithm of the large number or very large number instead of the number itself. Natural logs are particularly useful in physics and thermodynamics. Now, one thing I want you to remember is the rules of how to deal with logarithms mathematically. Of course, this gets covered way back in high school, but it might have been a while, and so it's worth taking a look at them and reviewing how to handle them. So remember, for logarithms, you've got the product rule, and that means that if you have the log of x times y, then that's going to be the log of x plus the log of y, okay? The quotient rule, which is that if you have the log of x divided by y, that's the log of x minus the log of y. There's power rule, which is that if you have log of x to the power p, that's going to be p times log of x. You can change base. We'll do that a little less often. But if you do that, log base a of x is log base b of x divided by log base b of a. Really not too useful. We mostly do with natural logs and don't change base in thermo. And then, of course, the equality rule we might use. If the log of x equals the log of y, then that means x equals y. That's pretty straightforward, I think. There's one other, and that's a thing to remember, and that's that in any base, the log of 1 is going to be 0, because if you want to get 1, you raise something to the power of 0, right? And then there's also the idea that the log base a of a is equal to 1. So, for example, the log base 10 of 10 is 1, because 10 to the power of 1 is 10, right? Or e to the power of 1 is e. So you can read more about that at this link here below if you need a refresher. So one new thing that we're going to be using in thermodynamics that you might not have seen before is Stirling's approximation. And that's because, as you might have noticed, in our discussions of Einstein's solids and the coin flip one, right, where you have the formulas for the multiplicities contain factorials. So we use a lot of factorials. But of course, factorials of large numbers are very large numbers, and very large numbers have a tendency to make calculators throw up, okay? Also some computer programs, okay? So we're going to use Stirling's approximation to help prevent computer and calculator barfing. So Stirling's approximation goes as follows. If you're taking a number of factorials, or for example n factorial, that's approximately equal to n to the n power times e to the minus n power times the square root of 2 pi n. So that's the approximation. Now, there's a proof of this in the appendix of Schroeder's thermal physics text. And you can look at that proof if you'd like. I'm not going to cover it in class, okay? We're just going to use it. And as a proof is in the pudding, what you can do is try it out, okay? So try doing 50 factorial, okay? 50 factorial, I calculated it using Excel, although heck, maybe Excel uses Stirling's approximation. 50 factorial is 3.04141 times 10 to the 64th, okay? So now you calculate 50 factorial using Stirling's approximation and see how close it gets. Okay, now, one thing I want to caution you about is Stirling's approximation works best when the numbers are big, right? If you have a little number, it won't work as well. Now, n factorial is assuming n is a large number, and then you're doing a factorial of it, like the number of moles, or the number of molecules, like 10 to the 23rd per mole, or something like that. N factorial is going to be a very large number. So we might need to use logarithms on it to make it easier to deal with, like log of n factorial. You might have also noticed that, your formulas for the multiplicities contain a lot of factorials, and the formula for the entropy is going to be Boltzmann's constant times the natural log of the multiplicity. So we're going to be taking the natural log of a lot of factorials when we're calculating our entropies, okay? So another useful approximation that's related to the approximation I just showed you, Stirling's approximation, is this, that the log of n factorial is approximately equal to n log n minus n. So for a proof of that, look here at the next line. The log of n factorial, okay, now we're going to plug in Stirling's approximation for n factorial into that equation. So that would be approximately equal to the log of n to the n e to the minus n square root of 2 pi n. Now, using the product rule for logarithms, that is equal to the log of n to the n plus the log of e to the minus n plus the log of the square root of 2 pi n. Now, the log of n to the n power is n times log of n. The log of e to the minus n is minus n, right? And then the log of the square root of 2 pi n, well, that you can approximate as going away, because once you take the logarithm of the square root of n, you're going to have a small number. And then n is a large number, and adding or subtracting a small number to a large number doesn't change the large number. So we can approximately say that the log of n factorial then is equal to n log n minus n. Okay? So those are some approximations that we're going to be using in the following lectures, and in fact for the rest of the course, for thermodynamics, because we're going to have these multiplicities that have these factorials in them, and then in order to get our entropies, we're going to have to take the natural log of those factorials. So there you go. I hope that was useful, straightforward, and you understood it, and as always, I'll see you in class.